Now we can do the homework, starting at 17 for section 2.3. 1 through 16 is all the theory of kind of how the chain rule works, but not that, illustrative in terms of applying the rule. So let me use the chain rule for all the derivatives that we have parentheses with exponents, and that's perfectly for problem 18. For problem 18, I'm going to think of the coefficient being 1, and I'm going to say the derivative is the exponent 2 times the coefficient 1 times the derivative of the contents of the parentheses. This is a symbolic way to write the derivative of the contents of the parentheses. The derivative of 8x is just 8. The derivative of minus 5 is 0. When the derivative is a monomial or a single term, I don't need a parentheses to put the derivative in. So exponent, coefficient, derivative of the inside of the parentheses times the original parentheses with the exponent lowered by 1. It's going to be 8x minus 5 to the first. Let me just multiply the 2 times 1 times 8 and get 16. Lower the exponent by 1 and get 8x minus 5 to the first. I don't need to write that exponent of 1. That's a perfect derivative for problem 18. 20 is a perfect setup for the chain rule itself. I have a constant times a parentheses with an exponent. So I'm going to find the derivative by multiplying the exponent times the coefficient times the derivative of what's inside the parentheses. The derivative of 5x is just 5. The derivative of 4 is 0. So the derivative of the inside of the parentheses is just 5 times the original parentheses with the exponent lowered by 1. Multiply the 4, the 3, and the 5 and get 60 for the coefficient of the parentheses 5x plus 4 cubed. These are simple one-step chain rule problems. Once the coefficient has a variable, then I'm stuck using the product rule, and that's a disaster. 22, simple chain rule. A constant times a parentheses with an exponent, that's a chain rule. So to do the chain rule, take the exponent 3, multiply it by the coefficient, multiply it by the derivative of the inside of the parentheses. That's the notation that tells me to multiply by find the derivative of that. The derivative of 5x is just 5. The derivative of minus 6 is 0. And then take the parentheses and lower the exponent by 1. This is going to give me the derivative, if I multiply those numbers together, is 30 times 5x minus 6 squared. You can't multiply 30 through the parentheses because you'd be doing multiplication before exponents, and it's better factored anyways. In 24, I'm going to need a parentheses when I insert the derivative because the derivative is going to be a binomial. So I'm going to sneak that coefficient of 1 that's implied in 24 and use the chain rule. So I'm going to go the derivative is the exponent 3 times the coefficient 1 times the derivative of 3x squared minus 5x plus 1. And because this derivative is going to have two terms, I need to put it in a parentheses. The derivative of 3x squared is 6x. The derivative of minus 5x is minus 5. The derivative of 1 is 0. And then multiply it by the original parentheses, 3x squared minus 5x plus 2, with the exponent lowered by 1. And it's not readable down here, but let me make it readable. I'm just going to multiply that 3 times 1 and get a 3. I'm not going to FOIL out any of these parentheses. I'm going to leave it factored. So this is the perfect answer. 3 times 6x minus 5 times 3x squared minus 5x plus 2 squared. That's the good position. This is the bad position. Problem 25. And let's maybe do 25 together because this is the problem I flubbed up on. So problem 25, I can't just use the chain rule because the coefficient has an x. I need to use the product rule. In the middle of doing the product rule, I'm going to do the chain rule. So I'm setting it for the product rule first. I'm going to do first factor, try to write the first factor down correctly, The first factor is 5x, and its derivative is easy. It's a first power term. Its derivative is just 5. The second factor is the bad one. It's 2x minus 4 cubed. To find its derivative, I'm going to need to use the chain rule. So let me find its derivative. That factor is 1 times 2x minus 4 cubed. I'm going to find its derivative. Because it's finding the derivative of a parentheses with an exponent, I need the chain rule. I'm going to go 3, multiply it by 1, and then multiply by the derivative of the inside of the parentheses. That's the derivative of 2x minus 4. The derivative of 2x is just 2. The derivative of minus 4 is 0. I don't need an extra parentheses here for the derivative of the inside of the parentheses because it's just a monomial. And then lower the exponent by 1. It's unfortunate that that has a common factor that I might feel the urge to factor out, but boy, I'd have to be careful to do that. So this derivative is 6 times 2x minus 4 squared. Now I'm set up for the product rule. In the middle of doing the product rule, I needed the chain rule. I'm going to cross multiply down, cross multiply up, put a plus sign between. So the derivative is 5x times 6 times 2x minus 4 squared, and then plus 5 times 2x minus 4 cubed. This is the derivative. Now it's just a matter of cleaning it up by pulling out common factors. The first common factor I'm going to pull out is the easy one. They both have a 5 I could yank out. So I'm going to get the derivative is 5, and then this x times 6 I'm going to write as 6x times 2x minus 4 squared plus 2x minus 4 cubed, taking both the 5's out as a common factor. Now I'm going to do a common factor of 2x minus 4 with the smaller exponent of 2. So to continue my common factoring, I'm going to pull out the common parentheses with the smaller of the exponents. That's going to be a 2x minus 4 squared. Inside the parentheses to the left of the plus sign, I'm just left with the 6x because I took that factor out completely. After the plus sign, I'm left with 2x minus 4 to the first power because I had 3 of those. I took 2 of them out, so I'm just left with 1. And this exponent of 1 makes it so I don't need that parentheses, and I can just write 2x minus 4 there. I'm going to combine the 6x and the 2x and get 5 times 2x minus 4 squared. I really regret doing that problem. Times 8x minus 4. There I can factor out a 4. There I can factor out a 2. Let me do those, but I'm not going to factor out a 2 when it's written as 2x minus 4 squared because I'll mess up. So let me think of this as being 5 times 2x minus 4 times 2x minus 4 times 8x minus 4. And from this parentheses, factor out a 2. From that parentheses, factor out a 2. From that parentheses, factor out a 4. This is going to give me y prime is 5. First common factor of 2. Second common factor of 2. Lastly, the common factor of 4. Factoring out a 2 from this, you'd be left with an x minus 2. Factoring out a 2 from this, you'd be left with an x minus 2. Factoring out a 4 from this, I'll go 8 divided by 4 and get 2, leave the x. 4 divided by 4 and get 1. Multiply these common factors up. 5 times 2 is 10, times 2 is 20, times 4 is 80, and get 80. I have a double x minus 2's, so times x minus 2 squared times 2x minus 1. That's reducing on steroids. Good to do. If you didn't catch out that factor of 2x minus 4, fine. Usually when I'm using the chain rule and the product rule together, I always do the double common factors. The integer common factors and the parentheses common factors. And then this just got kind of cutesy. It's correct. Maybe nice to do for somebody that's really comfortable with this, but maybe not for everybody. But getting down to this step right here, everybody should be able to get there. And then this nice cuteness would be nice to see, but you know, if factoring isn't your friend so much, if you stop there, I'd live with that. This is unusual to get these double common factors to pull out. I'm going to move on to 28, which is another evilness because it's parentheses with an exponent, so I know I need a chain rule, but I can't go directly into the chain rule because the coefficient has a variable. When the coefficient has a variable, I need to use the product rule. Product rule makes me take the first factor, in this case 5t squared, find its derivative, in this case 10t, and the second factor, in this case 4t minus 1 squared, and find its derivative using the chain rule. So this derivative, that is 1 times 4t minus 1 squared. To find its derivative, I take the exponent 2, multiply it by the coefficient 1, and then I multiply by the derivative of the inside of the parentheses. That's the derivative of 4t minus 1. The derivative of 4t is just 4. The derivative of minus 1 is 0. So that's the derivative of the inside of the parentheses. And then I multiply by the parentheses with the exponent lowered by 1. So this derivative is going to be 8. That's the 2 times 1 times 4 times 4t minus 1. Now I'm going to cross multiply, put a plus between, and call it my derivative. So my derivative is going to be the 5t squared times 8 times 4t minus 1 plus 10t times 4t minus 1 squared. Lots of common factorings. I can attack them any order that I want. I'm going to start doing one at a time. Between this 8 and that 10, I can factor out a 2. When I factor out a 2, the 8's going to turn to a 4, the 10's going to turn, ooh, ha ha ha. I don't even know what to say right now. I mean, I know what to do, but I'm not sure how to make it less complicated. Let me multiply this 8 and 5 real quickly because there's these two numbers, they both have a common factor with 10, and it's making my head spin trying to explain what to do. It's easier if I have the 8 and the 5 multiplied to explain what I'm about to do next. So let me rewrite this side as 40t squared times 4t minus 1. This is going to help my common factor explanation quite a bit. Otherwise, I'm not exactly sure what I was going to say. It was going to be jumbled. Between this 40 and that 10, I can factor out a 10. So I'm going to say g prime of t equals to 10. And then inside the parentheses, I'm going to take that 40 and divide it by 10 and get 4t squared. And then 4t minus 1. And then that 10's gone, so I'm just left with t times 4t minus 1 squared. Now I'm going to pull out a common factor of a t because in front of each parentheses there's a single t, and I take the smaller exponent. So I get g prime of t equals to 10, which is the first common factor, followed by a t, which is my second common factor. And then inside my parentheses, the 4 is going to remain. This t squared is going to go down to a t. I haven't dealt with the 4t minus 1s yet. I'll do it next. After the plus sign, that t is gone, but the 4t minus 1 squared still remains. Last common factor, 4t minus 1. 4t minus 1 squared, take the smaller of the exponents, and I'm going to factor out a 4t minus 1 to the first power. First common factor of 10, second common factor of t, last common factor of 4t minus 1. When I take the 4t minus 1 away from the 4t times 4t minus 1, I'm just left with a 4t. And after the plus sign, I had two of these, I'm just left with one of these. When I'm just left with one of these, I don't need the parentheses anymore. Now I'm just going to add those 4t's and get an answer of my derivative, completely simplified, and we usually completely simplify for these chain rules if I can, is 10t, it doesn't look like I have a right answer there, times 4t minus 1 times 8t minus 1. Feel good about this work. 5, 8, it looks good. I think this is just a mistake there. All right, let's do your problem 29 as opposed to my problem 30 because it's, tough. So let's do this combination. So on 29, it's multiplying. Both factors have a variable. I have to use the product rule. In the middle of doing the product rule for 29, I'm going to need the chain rule. So first factor in 29 is 6y minus 3. That's an easy factor, an easy derivative. The derivative of 6y minus 3 is just 6. The second factor, sometimes I'll call it the last factor, is 5y plus 4 quantity squared. For its derivative, I'm going to think of that coefficient of 1. And when I go to find its derivative, I take the exponent, multiply it by the coefficient, then I multiply it by the derivative of both terms inside the parentheses. The derivative of 5y is just 5. The derivative of 4 is 0. And then I lower the exponent by 1. So this derivative is going to be 10. 2 times 1 times 5 times 5y plus 4 to the first. So I do get the chain rule, but just not as my primary rule. My primary rule here is the product rule because I'm multiplying and both factors have a variable. So now I'm going to write my derivative. My derivative is cross multiply this way. 6y minus 3 times 10 times 5y plus 4. Cross multiply this way. Plus 6 times 5y plus 4 squared. It's probably, boy, I'm not happy with myself. With this, giving parentheses with common factors to start is just dumb of me. I've done it twice now, and it is what it is. Let me pull out a common factor of 2 from this parentheses just to make my life easier. So of 3, should I say. I'm going to pull out a 3. And make this parentheses 2y minus 1. And just like I did in the last problem where I struggled for my factoring, I'm going to multiply those constants together. It's probably the easiest way to attack the answer. So I'm going to multiply that 3 and that 10. And get 30 times 2y minus 1. Times 5y plus 4. The calculus is not grunge. The algebra to get an answer looking pretty is ridiculous. All right, now I'm set up where I can pull out common factors. So between this 30 and this 6, I can factor out a 6. So I'm going to say the derivative. I'm going to factor out a 6. From here, that 30, when I factor out a 6, is going to turn to a 5. I'm going to leave the 2y minus 1. I'm going to leave the 5y plus 4. After the plus sign, when I factor out the 6, I'm just left with the 5y plus 4 quantity squared. Now I'm going to pull out the common factor of 5y plus 4 to the first power. So I'm going to write my derivative is the first common factor 6 times the next common factor 5y plus 4 times, here I'm left with 5 times 2y minus 1. And here I'm left with 5y plus 4. I don't need the parentheses anymore because I no longer have an exponent. Let me clean up the inside of this parentheses and say the derivative is 6 times 5y plus 4 times 10y minus 5 plus 5y plus 4, clearing that parentheses. And now I'm going to add the 10y and the 5y, and I'm going to combine the minus 5 and positive 4 in that last parentheses to get the best possible answer, which may or may not match with my answer key because I don't know how intense I got in the factoring. This is the proper way to factor it. I don't know how proper I got because of this crazy 6y minus 3. Twice now I snuck that common factor in where I really shouldn't have. That's too advanced for a 212 class to make the factoring that intense. And I didn't realize that I did it, but I did it twice. So It is, I mean, it can come up. I shouldn't have made it come up twice in a 212 class. 220, yes. 212, no. Uggles coming up worst is when we have the chain rule and the quotient rule. And that's what we're going to have in 33 and 34. And then we'll do some equations of tangent lines, which will be friendly-ish. So, in 32, I have division. So, division implies the quotient rule. To do the quotient rule, I need to have the denominator and its derivative, and the numerator and its derivative. So let me try to figure out these derivatives. Well, the derivative of the numerator is just 0. I don't need to figure that out. For the denominator, 1 times 2x minus 9 cubed. How do I find its derivative? I use the chain rule. I take the exponent 3, multiply it by the coefficient 1, and then I multiply by the derivative of 2x minus 9. The derivative of 2x is 2, the derivative of minus 9 is 0. And then I lower the exponent by 1. So the derivative of this is going to be 6 times 2x minus 9 squared. Now let me set up for the quotient rule. The quotient rule, I multiply this way, that way, put a minus between for my numerator. So my derivative is going to be this, which is 0 times 2x minus 9 cubed, minus, multiply this in a nice order, 5 times 6 times 2x minus 9 squared, all over the denominator 2x minus 9 cubed squared. This piece in the numerator comes out to 0. This piece in the numerator comes out to 30 times 2x minus 9 squared. In the denominator, the nice way to simplify it is to multiply these exponents, and I get 2x minus 9 to the 6th. What I'm left with here is the derivative is minus 30 times 2x minus 9 to the 2nd power over 2x minus 9 to the 6th power. I could cancel out both of the 2x minus 9's in the numerator by taking away 2 of the 6 2x minus 9's in the denominator, bringing it down to 4 of those. My answer for 32 is going to be the derivative is negative 30 over 2x minus 9 to the 4th power. That's heady, but not quite as heady as 33 and 34. I'm saying let's skip 33 and 34. This feels like a little too much right now for our class when I'm looking at the level of difficulty. You can try 33 if you want. I won't put something like it on a test where you have to use the quotient rule, the chain rule, and the numerator also has an x. That just probably is, it's not that hard, but it's more than I think we should do right now. I want to bang out these horizontal tangent line problems because they're going to be important, because I sneak them on the test always. So I did one of these in an example. Let's do another one. I'm going to work on 36. Find all values of x where the tangent line is horizontal. For part A, I'm going to find the derivative, set it equal to 0, and solve for x. And then in part B, I'll do the work to get the equation of the tangent line, but I'm not going to do that just yet. So my function, if I look at it in problem 36, is 1, which I really don't need to keep writing that 1, but I'm just used to it. To find the derivative, I'm going to use the chain rule. Multiply the exponent by the coefficient, and then multiply by the derivative of the inside of the parentheses. The derivative of 3x minus 4. The derivative of 3x is 3. The derivative of minus 4 is 0. So that's the derivative of the inside of the parentheses times the parentheses with the exponent lowered by 1. So my derivative is 6 times 3x minus 4. I want to set this equal to 0 and solve for x. So I'm going to do 6 times 3x minus 4 equals to 0. I can get rid of this multiplication if I care to, but I don't have to. When there's an exponent with the factor, I can't get rid of the multiplication, so I'll pretend like I couldn't get rid of it. The factor of 6, because it doesn't have an x, doesn't give a value, or a value of x that makes the tangent line horizontal. And then the factor of 3x minus 4, I add 4 to both sides, and then divide both sides by 3. The answer to part A is going to be x equals 4 over 3. Can't see it written low, but it's down there. For part B, I have an x coordinate of a point, and I have a slope because horizontal lines have slopes of 0. So for part B, to find the equation of my tangent line, immediately I know the slope is 0 because all horizontal lines have 0 slope. I know that the x coordinate of my point is 4/3. I need to get the y coordinate of my point by plugging in 4/3 for this x. Oh, into that equation. I'm looking at this, I'm doing the math in my head and it wasn't working. So let me get the y. So my y coordinate of my point is going to be 3 times 4/3 minus 4 squared. That's just going to that x and plugging in 4/3. On my calculator, parentheses, 3 times 4 divided by 3 minus 3 squared. That's what that looks like. And, well, I messed up, minus 4. 3 times 4 divided by 3 minus 4 squared. That's what it looks like if you're not being not so bright. So my y is going to be 0. Now I can use the formula y minus the y coordinate of the point, which is 0, equals the slope, which is 0, times x minus the x coordinate of the point, which is 4/3. Left side simplifies to y because y minus 0 is y. Right side simplifies to 0 because anything times 0 is 0. My answer to part B is y equal to 0. Let's do one more, and let's actually do one of yours. Let's do problem 37 together. So this is your homework problem, but we can do it. And it's the last problem for the section. So for 37, find all values where the tangent line is horizontal. That's finding the derivative, setting it equal to 0, and solving for x. So for 37, I'm going to find the derivative using the chain rule. I'm going to take the exponent of 4, multiply it by the coefficient of 5, and then multiply it by the derivative of the inside of the parentheses. And I'm going to emphasize the inside of the parentheses is 1x plus 3. The derivative of the 1x is just 1. The derivative of 3 is 0. So the derivative of x plus 3 is just 1. And then multiply it by the original parentheses with the exponent lowered by 1. So the derivative is 20 times x plus 3 cubed. I don't need to write the derivative in my answer. I need to write what happens, what I get when I take the derivative and set it equal to 0. So I'm going to go 20 times x plus 3 cubed equals to 0. Then I'll go 20 equals to 0. And because that doesn't have an x, there's no solution. And then I'll do x plus 3 cubed equal to 0. And anytime I have a factor with an exponent equal to 0, it's sufficient just to set the inside of the parentheses equal to 0 and do that algebra. That only works when it's equal to 0. So my answer to 37a, the value x equal to negative 3 is the value of x where the tangent line would be horizontal. For 37b, because I know I'm finding a horizontal line, I know that its slope is 0. I know that the x coordinate of the point is negative 3. I just need to get the y coordinate. And I get the y coordinate by taking the x and plugging it in. So the y coordinate of my point is going to be 5 times negative 3 plus 3 to the fourth. I know that comes out to be 0, but let me make sure it does. 5 times negative 3 plus 3 to the fourth. The y-coordinate of my point is 0. And now just y minus the y-coordinate of the point equals the slope times x minus the x-coordinate of the point. The left hand simplifies to y. In the right hand side, no matter what you multiply by 0, no matter how complicated it is, it will come out to 0 as well. This will be the answer to 37b. 37a is x equal to negative 3. So that's everything that we need for the chain rule. In the next section, we're going to do derivatives of exponential functions and logarithmic functions. Technically, when we're doing those derivatives, we're using the chain rule, but I won't even hint at that. I'll just teach you a way to find the derivatives more or less like we found the derivatives here, just using a strategy that's going to be effective for our class. So let's pause this and we'll move on to 2.4 when we get to it.